Hi everyone, good evening. So we are in the session 9 of this ray optics, and we are discussing about the refraction, right? So in this we are looking at what? Refraction through a prism, correct? So already in the previous class we have discussed about the angle of deviation derivation. So what is this angle of deviation? Delta will be equal to what? I1 plus I2. I1 is the angle of incidence, I2 is the angle of emergence. I1 plus I2 minus A. A is what? The angle of the prism, which is also called as what? A is also called as the refracting angle of the prism. What is A called as? The refracting angle of the prism. Okay. So this is what is the deviation formula that we have derived in the last session. In fact, we also did this one. The A value, right, will be equal to this R1 plus R2. R1, R2 are the angles made by the light ray with the normals inside the prism. So R1 plus R2 will be equal to what? A. Now for a prism, right, the consideration that we'll have is generally the prism will be considered as isosceles, which means this side is equal to this side. That is what we'll be considering. Okay, our discussion will be for the isosceles prism. So here if you talk about where do we get the minimum deviation angle, so this is also something that we have covered in the previous session. So if you look at the graph of, this is an experimental study that you will also do probably if the schools reopen for the experiments, you might get a chance to do this. So for a prism, right, this is a very standard experiment that is there in the 12th syllabus, finding the minimum angle of deviation. So if you plot the angles of incidence I1 with the corresponding delta, we will see at a particular point the delta will become minimum. Now for any delta value, right, we will get two values of I1. For both these values, delta will be same. What these two values of I1 will correspond to? Basically, one is indicating what is the angle of incidence on one side, other is indicating what is the angle of emergence, because light will follow that principle of retraceability. The way it goes, it comes back in the same path. So two of these angles will correspond to what? This side one angle, that side another angle. Okay. Now when you come to this minimum deviation, right, both these I1 and both these values are merging, which means what? The minimum deviation will correspond to when this I1 is equal to I2. Incidence angle is equal to what? The emergence angle. Not only that, because of the symmetry, right, R1 also must be equal to what? R2. So in that case we will have, if you say that the R1 is equal to R2 is equal to R, 2R is equal to A, because R1 plus R2 is equal to A, right? From here we will get R is equal to A by 2. From here we will get R is equal to what? A by 2. And I1 is equal to I2, right? Let us call it as what? I. So 2I minus A is equal to this delta minimum. From here we will get the delta minimum plus A divided by 2. That is our I value. Now if you apply the Snell's law at the first interface, angle is I incidence, refraction is angle is what? R. What we will get is the relation. What is it? Mu will be equal to sine of, this is I. I is what? A plus delta minimum by 2 divided by, this is what? R. So this we will get by applying the Snell's law. So till this we have covered in the previous session. I am just trying to revise them. Okay, so the refractive index of the prism, mu is equal to what? Sine of A plus delta minimum by 2 divided by sine A by 2. So this is the relation between angle of the prism, delta minimum, and the refractive index. Now we can expect some questions based on this particular formula. So what is the formula? Mu is equal to what? Sine of A plus delta minimum by 2 divided by sine A by 2. We already done this derivation in the session 8. Now what we'll do is we'll look at some sample questions based on this. Okay. So look at this, guys. Look at this question. The refracting angle of the prism is A. What is the refracting angle of the prism? A. And refractive index of the material of the prism is cot A by 2. Means mu is given as what? Cot A by 2. Mu is given as what? Cot A by 2. In this, the angle of the minimum deviation is, means they are asking us to find delta minimum, delta m. Let us see who can find the answer. So what they are giving us, mu value they are giving us, they are mentioning A is what? A is the refracting angle of the prism, the top angle. And mu is given as what? Cot A by 2. From here we have to find what is the delta minimum. So look at this, guys. What is the relation we have? Mu, refractive index of the material of the prism, is equal to what? Sine of A plus delta minimum by 2 divided by sine A by 2. But mu is given as what? Remember, mu L is given as what? Cot A by 2, right? Cot A by 2 means what? Cos A by 2 divided by sine A by 2. So sine A by 2 we can cancel it off. Now look at this. What do we have? Sine of A plus delta minimum by 2 is equal to cos A by 2. We have to somehow get the relation between the angles, right? Left side we have a sine function, right side we have a cos function. How do we tackle it? We'll try to change. Right side, what is their cos, right? Cos can be written as what? Sine pi by 2 minus A by 2. Cos theta is equal to sine pi by 2 minus theta. So left hand side is sine A plus delta minimum by 2. Right hand side is what? Sine pi by 2 minus A by 2. From both of them, right, we can say the angles inside are equal. If we equate the angles inside, what we'll get? A plus delta minimum by 2 is equal to what? Pi minus A by 2. Okay, so 2 is cancelled. 2 and 2 will be cancelled. We will take the A to the right side. It will become what? Minus A. So delta minimum is equal to what? Pi minus A. One more minus will go there. What is it? Pi minus 2A. That is our delta minimum. Check it up, students. Pi is what? 180, right? So delta minimum must be what? 180 minus 2A. Check it. How many of you got the answer? The angle of minimum deviation, right, should be what? It should be 180 minus Rachel, Shivani. None of you are typing the answer. I am assuming you would be able to get it. So these kind of questions, these are straight questions, right? We can expect on the relation, refractive index, angle of the prism, and then the minimum deviation angle. What is the formula? Mu is equal to sine of A plus delta minimum by 2 divided by sine A by 2. So for this, what is the answer? It is option D. Delta minimum should be equal to what? It should be equal to 180 minus 2A. Delta minimum should be equal to what? 180 minus 2A. So check it, students, whether you got the answer or not. The only thing is here, looking at that trigonometric function conversion. Like how do you convert the both trigonometric functions into one form? Okay. So I'm assuming we can move on. Now the relation that we have is what? Mu is equal to sine of A plus delta minimum by 2 divided by sine A by 2. If you have small angle prism, this is an assumption. In reality, there will be no small angle prism, but generally if the prism angle is somewhat less than or around 10 degrees, right? 10 degrees is also a little bit higher only, but broadly, if it is less than or around 10 degrees, we will consider this small angle assumption. In terms of degrees, what is the maximum up to which we can go? We should look at the angles which are less than or around 10 degrees. Then we can go with this small angle prism assumption. What do you mean by the small angle? If you look at the prism angle, right, it will be small value. Now delta minimum, right, minimum deviation will be small only. Minimum deviation value will be what? It will be small. So if A is small and delta minimum is small, remember, if the angle is small, then sine theta can be approximated to what? Theta. So under this assumption, right, mu can be approximated as what? Numerator will have A plus delta minimum by 2. Denominator we will write as what? A by 2. Now here we have to keep one thing in mind. Angles must be in radians. When I do this, right, we should keep one thing in mind, that the angles must be in radians. Okay. If they are not in radians, means we know how to convert them in radians. How do we convert angle in degrees into radians? Into pi by 180. That's it, right? Now look at it. This 2 is cancelled. So mu, for now I'll equate it. Mu is equal to what? A plus delta minimum by A. I'll cross multiply. Left hand side I'll have mu into A is equal to A plus delta minimum. I'll take the A to the left side. Mu A minus A is equal to delta minimum. So look at this, guys. Take A common out. Mu minus 1 into A is equal to what? Delta minimum. So we are getting a delta minimum simplified formula. When we can use it? We cannot use it for any prism. This can be used only for what? The small angle prism. What is the delta minimum value? Mu minus 1 into A. What is the delta minimum value? It will be what? Mu minus 1 into A. When we can use it? We can use it only for the small angle prism, not every time. Okay. Now, Akash. Okay. So is it clear, guys? For a small angle prism, what is the minimum deviation formula? It can be written as what? Mu minus 1 into A. Here we are doing that trigonometric simplification. For small angles, sine theta is approximately equal to theta. That's it. Okay. Now, if you look at one thing is prism will cause deviation. If you passing one single ray of light, means it will deviate it. That we are able to see. That angle of deviation we are able to see. But what a prism will also do is, like, look at this visualization, right? What is happening? Prism will be able to disperse the white light. If you are passing white light, means when the white light comes out of the prism, right, you will see that there is a dispersion. Dispersion means what? It is like, the splitting. And when you carefully observe it, right, maybe, in NEET kind of examinations, we can expect these kind of reasoning questions. If you carefully observe it, how the splitting is happening? This is the original path, right? This is the original path. From the original path, if you observe it, red is what? Least deviated. Red is the least deviated. That is the original path. From there, what is the least deviated? Red is the least deviated. Which one is having the highest deviation? Violet. Violet has got the highest deviation. Red has got the least deviation. Violet has got the highest deviation. Now, why is it happening? There must be a reason, right? So the reason is, when we look at, assume this is a small angle prism. What is the delta formula? Already we have it. Mu minus 1 into A. Which means, for different colored lights, for red, because A is same for all these lights, where should the difference be coming from? Mu only it should be coming, right? For red, the mu value is different. For orange, the mu value is different. For green, it is different. Blue, it is different. Indigo, it is different. Violet is different. So far, we have not talked about this idea. We are assuming that for all electromagnetic radiation, refractive index means it is the same value, like that we are assuming. But the detailed study of how the refractive index will depend upon a particular wavelength, it is a little bit beyond our syllabus. But what we should know is that the refractive index value will depend upon the corresponding wavelength. The refractive index value will depend upon the corresponding wavelength. How it will depend upon the corresponding wavelength? We have this empirical relation, which is called as the Cauchy's formula. Okay, we don't need to bother too much about remembering this Cauchy's equation, but we need to just get that idea. It's an empirical relation. So A, B, C are called as parameters. They'll have specific values, but importantly, look at it. What is the relation? Mu is equal to what? A plus B by lambda square plus C by lambda power 4. Means we can clearly see that mu, it is not like it is proportional to 1 by mu, but the relation is what? It's an inverse relation. Means if the, not mu here, it is lambda. The mu is having an inverse relation with lambda, which means what? If the lambda is increasing here, what is going to happen to the mu value? Mu will decrease. Now for the red, because among the visible, right, red has got the highest wavelength, which means the corresponding refractive index for the red will be the least. When the mu is least, look at the delta formula, right? Delta is what? Mu minus 1 into A, right? When mu is least, the delta for that red will be also least. For the violet, the other extreme, lambda is the least value. When lambda is least means mu violet will be highest. So delta violet will be what? Mu violet minus 1 into A. So this is going to be highest. Red delta will be least. That is why here this is what is the delta R, right? This delta R least. This is delta violet. Okay. Now the dispersion, right, is happening because of what? It is happening because different colored lights, they will possess different values for the refractive index, and that we'll understand by using this Cauchy's empirical relation. But here the idea is what is important for us, not the exact formula of the Cauchy's equation, because we may not get questions exactly asking us to substitute the values and get etc. But the basic idea is what is important to us. Now here when we look at the path of the violet and the red, they are like the extremes. Violet and red path are the extremes. The mean path is taken as yellow. So the deviation of yellow, right, is also called as what? The mean deviation. So deviation of yellow means what? It will be mu yellow minus 1 into A. This is called as what? Mean deviation. So mean deviation is referred to what? The deviation of the yellow color light. Okay. And here sometimes, right, we will be given the refract index of the violet and refract index of the red. They'll give us refract index of the violet and refract index of the red. Then we will take the refract index of the yellow as the average of both these values. If they are not separately giving us yellow refract index, right, what we'll have to do? We have to take the refract index of the yellow as what? Average of the violet and red. Okay, so this is something that we need to keep in mind. Mean deviation means what? The deviation shown by the yellow color light is called as what? Mean deviation. Okay, and sometimes if they are not giving us the refract index of the yellow means we will take it as what? The arithmetic average or the mean value of the violet and red refract indexes. That's it. So this is the concept of the dispersion through a prism. Okay, now the dispersion of the white light, right, is what will cause the chromatic aberrations. So what is the word that we use? Whenever any optical instrument we are using, if there is this dispersion of the white light happening, so what is that phenomena going to be called as? Chromatic aberrations. Means the image formation or anything, right, because of red will be different from that of the violet. So you will see that when there is a dispersion means different components of the white light will behave differently. So any optical instrument you have this kind of phenomena, right, we will say what? There are chromatic aberrations. Chroma means what? Color, right? The splitting is happening means that is what we will refer to chromatic aberrations. Okay. Now in this we have one more important term which is called as a dispersive power. So dispersive power of a prism. Dispersive power of a prism. Generally we will represent this with the symbol omega. What is the symbol that we use for dispersive power? Omega. So like we were seeing in the previous visualization, right, this is the delta R. Mean deviation is given by delta yellow. Highest deviation is what? Delta violet. Now from red to violet, if you want to measure this angle, from red to violet, if you want to measure this angle, so what is this angle going to be? The delta violet minus delta red. So if you subtract, look at this, if you subtract from the delta violet value from this one, right, if you subtract this, means the remaining is what? The spread. The spread is also called as what? Angular dispersion. What is the spread called as? Angular dispersion. How do you measure it? The deviation of the violet minus deviation of the red. This is called as what? Angular dispersion. So angular dispersion will be what? Delta violet means what? Mu violet minus 1 into A. So here we are going on with the, which one? Small angle prism assumption. All these things we are continuing with the assumption of the small angle prism. Okay. Delta violet means what? Mu violet minus 1 into A. Minus delta red means what? Mu red minus 1 into A. Look at this. This is what? Mu violet into A minus A. Minus mu red into A. Minus of minus will become plus A. So plus A minus A is cancelled. What is it? Mu violet minus mu red into A. This is what is our angular dispersion. So what is the angular dispersion? It is the spread between that red to violet. That is what we call as the angular dispersion. Okay. And the dispersive power. Dispersive power is defined as, this is how we will define the dispersive power. Dispersive power is defined as, omega is defined as the angular dispersion divided by the mean deviation. How do you measure the dispersive power? It is what? Angular dispersion divided by the mean deviation. What is angular dispersion? Mu violet minus mu red into A. That is the angular dispersion, right? Mean deviation means what? Mu yellow minus 1 into A. Already we talked about it. Mean will be what? The one that is corresponding to yellow is called as what? Mean. So angular dispersion divided by the mean deviation, that is what will be the dispersive power. So look at it. A will be getting cancelled. So for the small angular prism, right? For the small angular prism, the dispersive power we will see is what? Independent of the prism angle. So these kind of questions we can expect in the reasoning type of areas. For small angular prism, right, the dispersive power will be independent of the prism angle. But what is the value? Mu violet minus mu red divided by mu yellow minus 1. Okay, so this is the formula that we need to keep in mind. This is what the dispersive power for a small angular prism. So here we are going through some set of important derivations or the standard results. All of this we are discussing by using what? By using the small angle prism. So that is the assumption that we are going on with. So even the previous case also, when we are using these mu minus 1 into A for any whether it is a red or a yellow or a violet, when we say that the delta is mu minus 1 into A, what is that formula for? The formula is basically for what? Small angle prism. Okay. So this is about angular dispersion. So what are the things we have? Angular dispersion. These terms are important. What are the terms we are having? We have one term, that is mean deviation. Then we have angular dispersion. Then we have dispersive power. Okay, so when we get questions straight on this formula, right, we should not be missing out the numericals. Then when you make a combination, of two prisms inverted with respect to each other, when you make a combination of two prisms inverted with respect to each other, means what? This is prism 1, this is prism 2. They are inverted with respect to each other. Now look at this. If you are passing the light ray like this, it will get refracted through the prism 1. Now when the prism 2 is inverted, right, the phenomena should be exactly in the counter direction. The phenomena should be exactly in the counter direction. So as a result of it, right, when you look at what will be the overall outcome, the overall outcome will be what? The overall outcome will be given by the combination of both the effects. Combination of effects from both the prisms. It will be given by what? The combination of effects from both the prisms. Okay. Now, what do you mean by the combination of effects from both the prisms? The prisms are inverted. So here, say for example, in case of the prism 1, what is the mean deviation? Mu minus 1 into A. So here mu will be referred to as what? The mu for the yellow. Mu is what? This average mu, that is the yellow color. This is what? Mean deviation, right? Whatever is the deviation of the yellow light is what we call as the mean deviation. So here we'll have to keep that the prism angle is A, right? So A is coming. Now what about the mean deviation in prism 2? So here the deviation is going to be exactly in the opposite direction. So we have to take it as what? Minus. Minus. Here if you say that the refractive index is mu1, let us say the second prism refractive index is different, let us say it is mu2, then it will be what? Minus of mu2 minus 1 into A dash. Why are we keeping the minus? Because it will be exactly in the counter direction. So overall mean deviation means what? Overall mean deviation will be what? This mu1 minus 1 into A, we have to add it, mu2 minus 1 into A dash. This is the overall mean deviation. Now sometimes if the parameters of the prisms are adjusted, we can have a possibility of having no average deviation or no mean deviation. We can have a possibility of having mean deviation to be equal to 0. That is possible. And that situation is what is generally called as dispersion, because in that case we may have a dispersion. The light might undergo dispersion. We will have dispersion, but there will be no mean deviation. Dispersion is going to be there, but there will be no mean deviation. And such a possibility will come when this overall mean deviation is simply equal to 0. So that situation is generally called as what? This is a very standard word that is used. So what is the wording that is used? It's called as what? Dispersion with no average deviation. So in some textbooks we will also call it as what? We will also call it as dispersion without deviation, like that. Means what? The mean deviation, overall mean deviation should be 0, that's it. Means what? Mu 1 minus 1 into A should be simply equal to what? We take it to the right side. It should be equal to mu 2 minus 1 into A dash, that's it. So whatever the deviation produced by the prism 1 in one direction, right, should be countered by the prism 2 in the other direction, that's it. Okay, so numerically here whatever is the mean deviation value should be same as the mean deviation in the other case numerically, but because they are inverted with respect to each other, one side the deviation is, say for example, in one way, other prism will counter it. Magnitude wise or value wise they should be same. Okay, so this condition, right, what is the condition? The numerical value of the mean deviation in the prism 1 should be equal to numerical value of the mean deviation in the prism 2. What is it condition called as? Dispersion without deviation. What is it called as? Dispersion with no average deviation or dispersion without deviation. Okay. Hope it's clear, guys. So it says the condition. Then we can have one more possibility. What is it? We can have a deviation with no dispersion. Just the other way. So we can have a deviation. Means overall can give us some mean deviation. The overall combination of the prisms can give us some mean deviation, but no dispersion. Now look at it as it is. What is the angular dispersion here? Delta V minus delta R. In case of the prism one, what is the angular dispersion? That is mu violet minus mu R into A. This is all for the prism one. What is the angular dispersion in case of the prism 2? Here I am going to use a different notation. Mu violet dash for the second prism minus mu R dash into A dash. Second prism, everything we are using dash. Okay. So this is what is the angular dispersion. No dispersion means what? Whatever is the angular dispersion created here, that should be counted on the second prism case. That should be counted. Anyway, it is inverted, right? So when it will be counted? It will be counted when the numerical values are same, isn't it? When the numerical values are same, it is going to be counted. Means what? Same like the previous one. But here we are equating what? In the previous case, we were equating the mean deviation. Here we are equating the angular dispersion. That's it. Mu V minus mu R into A should be equal to what? Mu V dash minus mu R dash into A dash. In that case, what is the phenomena we are going to have? We'll have no dispersion, because whatever the dispersion caused by the prism 1 is counted by the prism 2. But we may have a deviation. We are not commenting on the deviation. We may have a deviation. Okay. If both of them are happening means what? If both of them are happening, what is it? Then it will be the combination of the prisms with no dispersion, no deviation. When it will be happen, you tell me? When you have two identical prisms made up of same material. Think about two identical prisms made up of same material. In that case, what? Mu values will be same. A is same everywhere. So we will have mean deviation. Overall mean deviation will be 0. Dispersion also will not be there. Okay, that is the reason why if you take a combination of prisms, identical prisms, as it is like this. Prism 1, prism 2 exactly identical, reverse. When you pass white light, you will see when the white light is coming out of the prism 1, it will be dispersed. But when it is coming out of that second prism, right, you will see it again come like a white. Okay. And the deviation also will not be there. Means what? Whatever is the original incident ray, the final emergent ray also will be in the same path. Emergent ray also will be in the same path. So these are the two cases. One is what? First one is no deviation. So if you want, just remember it like this. No deviation. No deviation case means what? Mean deviation of the first prism is equal to mean deviation of the second prism. That is the formula. No deviation. No dispersion means angular dispersion of the first prism, numerical value, should be equal to the angular dispersion of the second prism. That's it. And we have to keep the prisms as what? Inverted. When we will achieve both? When they are after all identical prisms as it is. Think of two prisms identical, made up of same material, same dimensions. One is upright, other is inverted. Then we will have no mean deviation, no dispersion. Okay. So we look at what kind of questions can be asked on this. That is important. Look at this. A thin prism having refracting angle, means this is the angle of the prism A. 10 degrees is made up of glass of refract index 1.42. This prism is combined with another thin prism of glass refract index 1.7. This is second prism. So this is mu, means this is what? Mu dash, second prism. This combination produces, this is the thing that we have to underline. What is it? Dispersion without deviation. So we have to focus on what? Without deviation, means deviation is 0. Mean deviation is 0. The refracting angle of the second prism should be how much? What we are supposed to find here? We are supposed to find what is the refracting angle of the second prism. It's a straight formula, right? Already we have derived it. So we know already we should be keeping the prisms like what? If this is the first prism, angle is A, refract index is mu. How we should keep the second prism? Second prism should be kept inverted. With respect to first, we should keep it like this. No, we should keep it inverted. Like this we should keep. This is A dash, mu dash. They're asking us what? without deviation means mean deviation here. What is it? Mu minus 1 into a should be equal to the mean deviation there numerically. Mu dash minus 1 into a dash. For the first one, what is the mu? 1.42, right? So 1.42 minus 1 into a is what? 10. Should be equal to mu dash is what? 1.7 minus 1 into a dash. 1.42 minus 1 means what? 0.42. 0.42 into 10 is equal to 1.7 minus 1 means 0.7 into a dash. So this is what? 4.2. 0.42 into 10 means what? 4.2. So 4.2 is equal to 0.7 into a dash. We will bring it to the left side. 4.2 by 0.7. That is a dash. So what is 4.2 by 0.7 means? It is like 42 by 7, right? What is 42 by 7? 6. Check it, students. What must be the answer we should get? We should get the answer as what? 6 degrees. That is the refracting angle of the second prism. I'll just wait for a while. Those who got the answer, you can confirm whether you're able to get it or not. So these two conditions are important. What are the conditions? Dispersion without deviation. If you are confused with these words, means just remember it like this. Without deviation. Remember that without deviation means what? The deviation in the first prism is numerically equal to deviation of the second prism. Without dispersion means what? Angular dispersion of the first prism is equal to numerically equal to angular dispersion of the second prism. That's it. So in this question, without deviation means what? Mean deviation of the first prism is numerically equal to mean deviation of the second prism. That's what we are doing. Okay, so you have to confirm, guys, whether you are able to get the answer or not. Okay, see here I want to, so I'm assuming, I'm just waiting for you guys to respond in terms of your answers, whether you're able to get it or not. Okay, I think good enough. Some of you are able to get the responses. Here I want to mention one more word. This is important. Just remember, when they say that the combination of prisms is producing achromatic light. As we said, chroma means what? Color. Achromatic, combination of, not lenses. I mean, the word can be used for lens also. It can be used for prism also. It can be used anywhere. When you see the word achromatic behavior means what? Chromatic phenomena. We can see the colors when there is a dispersion. When they use the word achromatic, A is what? Negative prefix, right? Means what? This indicates no dispersion. So when they say, instead of using the word no dispersion, right, they can use the word in the question, they can give it like this. The combination of the prisms is giving us achromatic light. Means in that case, what we have to take? No dispersion is what you have to take. Because the dispersion is there means you can see the colors, chromatic. Achromatic means overall there is no dispersion. So these kind of things also we have to be taken care of. Okay. So this is broadly, what we have to cover in terms of the prisms, and of course we can, as we go on, we can solve some more problems on the prism, trying to understand what modifications can be done to the prism. Like one of the very standard models is a prism. We are assuming that each and every face is what? Transparent. We are assuming, prism, each and every face is what? Transparent. We may have a phenomena where, we can silver a face of the prism. Then as the light rays, they come in second side, they cannot refract. They will undergo what? Reflection. So we can make some modifications. This is one very standard modification that can be done to the prism. So as such, the basic things with regard to the prism we have covered. But what modifications can be done? Instead of having all the faces transparent, we can silver one face means at that face no refraction, but there will be reflection. The behavior itself will change. Whatever the behavior of the prism we discussed so far, that itself will be changing. Okay. So we can look at the specific problems once we cover the topic. We'll look at some questions on that. In fact, if you look at previous year JEE Advanced, you will see some questions particularly on this modification of the prism. Okay, we'll talk about those kind of questions a little later, but the base part of the prism and the behavior of the prism in terms of showing the refraction phenomena, that is what we already covered so far. Now the second part of the refraction, and probably another important area, is refraction at a spherical surface. Already in case of reflection, right, we talked about it, like the spherical mirrors. We talked about the spherical mirrors, right? So two examples we have taken. One is if the light is getting reflected by the surface which is bending inwards, we call it as what? A concave mirror. If the light is getting reflected by a surface that is bending outwards, we call it as what? Convex mirror. So we talked about the spherical mirrors. Now we look at refraction at a spherical surface. So far when we looked at the examples, right, refraction through a rectangular glass slab. What is the interface here? It is a plane interface between the air and the glass. What is the interface? Plane. Even in the case of the prism also, right, look at this prism also. What is this interface? The surface is what? It is a plane surface. Even the other examples we talked, when the light is going from air into water or from water to air, look at this in those examples also, right? The interface means what? The common boundary between the air and the water is what? Flat. It's a plane surface. But we can look at the refraction happening at the spherical surface, and from here only, right, we will go into the idea of the lens. So lens will be discussed from this concept of refraction at a spherical surface. So look at it generally when we talk about the spherical surface, like the way we have discussed in the case of the mirrors. Think about it here. If we have the object, so our assumption is what? Generally, we'll keep our objects on the left side. So if the object is emitting these light rays, they'll come to this boundary. Look at this. This is what is a spherical boundary. The light rays get refracted. When the light rays get refracted, you would see that the refracted rays, these refracted rays, they will lead to the image formation. Just like the reflected rays lead to the image formation, refracted rays also can lead to image formation. So we see here what? The object facing is what? It's a concave. In this case, the object facing side is what? It is a convex. So here also there will be refraction. Now through refraction, right, at a spherical boundary, what we will be able to see? There will be an image formation. And here the refraction at a spherical surface, right, the main important thing for us to study is going to be the image formation. And that is what we'll study later in detail when we talk about the lenses. So how do we see the image formation? Because of the refraction at a spherical surface. Further, when we have the study of image formation, right, we have, like in the case of reflection also, we discussed about it. We have two methods, right? One is what? One is, we'll follow the ray diagram method. One is what? We can follow the ray diagram method. Like we'll follow the path of the refracted rays and see where they are converging or where they appear to diverge from. Ray diagram method. Second method is the equation method. First is what? The ray diagram method. Second is the equation method. So if you look at refraction at a spherical surface, right, the equation method, we will have to use the sign convention like the way we do in the case of the reflection. So the direction in which the light rays starting from the object come, reflection also same thing, right? The light rays, we assume they are coming from the left side onwards, left to right, that is the direction we take, right? So this direction we will take it as what? The positive. The path horizontally, right? What is the positive direction? The path of the original light rays, that path is taken as what? It is taken as the positive. Okay. If you try to measure distances in the opposite direction, then we will have to take those as a negative. Like from the surface, when you measure the object distance, because where do we keep our objects? Objects are kept in the left side, right? So you see, we are measuring in which direction? We are measuring in the opposite direction to the path of the light rays. Means, like in the case of the reflection here also, the object distance, u will be what? U will be the object distance. Object distance will be what? Negative. Now for the spherical surface, if you think about where the center of that spherical boundary will lie, that is called as what? The center of that spherical interface. And the radius of that particular spherical interface will be called as what? The radius of curvature. So here in this case, right, where is this center? Center is on the left side. So when you measure the radius, we will have to measure to the left side. So in this case, the radius of curvature is going to be taken as what? Negative. Whereas in the second case, this is the first case. Second case, look at it. So here, this is the spherical interface, right, where the center will lie somewhere on the right side. So from the boundary, we will have to measure it to the right side. So that is the reason why the radius of curvature will be what? Positive. So in the case one where the concave side is facing the object, the radius of curvature will be negative because center will be on the left side. Second case where the convex side is facing the object, in that case the center of curvature will be on the right side. That is the reason why radius of curvature will be positive. This is something that we are used to. Okay. Now if the position of the image is indicated by the image distance, same notation, V is the image distance, the one that we are used to in the case of reflection. We have a relation between the object distance U, image distance V, radius of curvature, and the refractive index values of both the medium. So here light rays are coming from the left side, there is a medium, right side there is a medium. We'll have a relation between what? The object distance, image distance, radius of curvature with the refractive index values of both the medium. Okay. So what is this relation? So this relation is what we will be using to find the position of the image or to know where exactly the image will be formed. Okay. So the equation will be same for both of them. Whether we have the spherical boundary facing the object concave shaped or convex shaped, whichever case, the equation will be same. So what is this? Mu2 by V. So after refraction, the light rays will get into what? Second medium. For that, we will take the refract index as what? Mu2. Mu2 by V. V is what? The image distance. Minus mu1 by mu1 is what? The original rays coming from the object. The medium in which they are present is the medium for which we take the refract index mu1. Mu2 by V minus mu1 by U will be equal to what? Mu2 minus mu1 by R. Okay. So we can derive this result, but here we will just take it as an formula, and then we will try to see how we can apply this formula to find the actual image position. Okay. So what is the relation? Mu2 by V minus mu1 by U is equal to what? Mu2 minus mu1 by R. So we will cover this derivation also separately. So this will be again coming from the way we normally do the derivation using the geometrical behavior of light rays based on the angle through which they are deviated, etc. We will be able to do the derivation. We will do it separately, but here we look at the result. What is the result? Mu 2 by V. Mu 2 is what? The second medium where the light rays are present after refraction. Mu 2 by V minus mu 1 by U. Mu 1 is the first medium where the original light rays are present, is equal to what? Mu 2 minus mu 1 by R. So we have to use it along with the sign convention. We have to use the equation along with the sign convention. Let us just look at one question and then we will be able to get that. Look at it. Find out the position of the image formed. So you can see here, what is it? This is like, which side is facing that object? Concave side is facing the object, right? Means, look at this. U will be equal to what? 5 centimeter we are measuring to the left. Means U will be equal to what? Minus 5. What about R? R they say 10, but where is the center of curvature going to be? Left side, right? So R will be what? Minus 10. Mu 1 is 1. Here they are using a different notation for the refractive index because refractive index can be either represented by the symbol N or mu, whichever. So mu 1 is what? 1. Mu 2 is what? 1.5. What is the formula? Mu 2 by V minus mu 1 by U is equal to what? Mu 2 minus mu 1 by R. So mu 2 is what? 1.5 by V minus 1 by U. U is what? Minus 5 is equal to mu 2 minus mu 1. 1.5 minus 1 by R. R is what? Minus 10. So 1.5 by V. This is what? Plus 1 by 5. This is 0.5 by 10. Minus is there, of course. Okay. So what is this? This is minus 1 by 20. Now 1.5 by V is equal to what? The 1 by 5 will go to the right side. Minus 1 by 5 minus 1 by 20. What is it? If you take an LCM means, LCM is what? 20, right? So we'll have minus 4 minus 1, which is minus 5 by 20. Minus 5 by 20 means what? Minus 1 by 4. So I'll write it at the top. 1.5 by V is equal to what? Minus 1 by 4. Cross multiply. Then we'll get 1.5 is equal to 4 is minus V. 1.5 into 4 is what? 6 only, right? 6 is equal to minus V means V is equal to minus 6. Since everything is in the centimeters, right? V also will be in what? Centimeters. V also will be in terms of what? Centimeters. So check it, guys. What should be the answer? V should be what? Minus 6 centimeter. You have to confirm whether you are able to get it or not. V should be coming as what? Minus 6 centimeters. Means what? Just look at the significance of it. V is coming as negative. It's coming as negative means what? Where is the image formed? Distance is measured negative means what? In which direction is going to be taken? From that surface it has to be taken towards the direction opposite. This is the direction of the light rays, original light rays, that is positive. Negative means what? We should measure opposite. So object is 5 centimeter means this side we should go 6 centimeter. This is where the image is formed. It is not like always the image will be formed on the right side. Image can be formed on the left side also. We'll talk about the nature of the image. In a little while we'll talk about what is the nature of the image. Remember, in the case of the reflection also we have said, when the image is formed on the right side we'll have one type of nature. When the image is formed on the left side we'll have another type of nature. Whether the image is a real image or a virtual image, we'll talk about the characteristics in a little while, but this is how we will be able to use the equation. So the equation will be able to give us the position of the image. Okay, clear? So this is the refraction through the spherical surface. In the next session what we'll do is we'll start discussing a little bit more about it. How do we find the image characteristics, and also from this how do we understand the refraction through a lens. Okay, so the refraction through lens can be understood by using the concept of refraction at a spherical surface. Okay, so we'll talk about it in the next session, and try and practice some questions on prisms, because prism we have probably covered in detail. So you can work out some questions and maybe let me know if you have any difficulties in solving any specific questions. Okay, we'll see in the next session, guys.